Now let's look at absolute extrema with an example where the function is a rational function. In this particular case, we've got the rational function f of x equal the quantity x plus 3 over the quantity x minus 3 on the closed interval from minus 4 to 4. Now, earlier I had mentioned that if you have some special cases, there are some pretty easy procedures for finding the absolute extrema. Rational functions are seldom, if ever, going to satisfy those conditions. Even though this is a closed interval, the vertical asymptote is going to cause a discontinuity that's very seldom going to allow that to satisfy the earlier conditions. So one of the things I suggested when that happens is that you might just sketch the graph. Now, this is not a discussion of graphing rational functions, so what I want to do is bypass the graphing part under the assumption that you have already dealt with that or that you can go back and look at it. But I will point out a couple of things. First of all, this rational function has a vertical asymptote where the denominator is undefined, and that's at x equal to 3, so I drew in the vertical asymptote. And because the degree of the numerator is the same as the degree of the denominator, there will be a horizontal asymptote at the ratio of the coefficients of the highest powers of x. So you've got an understood 1 here and an understood 1 here, and 1 over 1 is 1. So you have a horizontal asymptote at y equal 1. We're not covering the topic of graphing rational functions, but I do feel like I should mention at least that much. And at this point, you might just plot some points. And again, I picked out some representative points and plotted them on here already. I might say that if you really understand the topic, you could probably just stop here and not even graph the points and figure out what's going to happen, because you've got a vertical asymptote here and a horizontal asymptote here. And if you're familiar with graphing rational functions, you're probably going to realize that that vertical asymptote is going to have part of the curve either rising here or going down here. Now, if it rises here and goes up toward the asymptote there, there's not going to be an absolute maximum. If it goes down here, there's not going to be an absolute minimum. If it rises this way, there's not going to be an absolute max. If it rises this way, it's not going to be an absolute min. And if it approaches the horizontal asymptote, there's not going to be an absolute min, because that is essentially getting closer and closer and closer, but there is no lowest value. So it seems to me that it's pretty apparent, just without even plotting the points, that there's not going to be any absolute extrema. But if you're not convinced by my argument, then I would suggest you plot some representative points and notice that at minus 4 you get 1/7, so I plotted it right there. At minus 2 you get negative 1/5, which is about right there. At 0 you get minus 1, there it is. At 2 you get minus 5, there it is. At 4 you get 7. At 6 you get 3. So you can sort of see what's happening. You've done these before, so none of this should be a brand new idea to you. You can see what's happening with this graph. And over here again you can see it. So you have to do as much work as you need to convince yourself that because this graph is going up along that vertical asymptote, there is no absolute maximum, and because the graph is going down along the vertical asymptote, there is no absolute minimum. So simple answer is there is no absolute extrema at all. No absolute maximum, no absolute minimum. So I would suggest with rational functions you at least sketch out the asymptotes and then either argue from what you know about what a graph looks like, or actually plot some points and convince yourself of the final result.